kill this. Let's see. Okay, that's actually pretty readable. And I want to make this tiny. Cool. Move that out of the way. Okay. Well, you should be able to see.
Whoops.
Oh,
All right.
the Zoom controls are so horrible. Where's my presentation? There it is.
Okay.
Cool.
So, hi everybody. I think our YouTube live is also live right now. I hope so. And yeah, welcome to the last chat of the lecture series this semester that the Hub is organizing. I'm Mira, the president of the Hub. What you're seeing on your screens right now is the beginning of our presentation slash lecture slash workshop. Ismail will explain more on modern C++, memory and management. It looks amazing. Let me give you a little bit intro about Ismail. So he's currently a Hub member and he's a very advanced professional, I dare say so. He can explain some more in a second. And yeah, he will tell us more about memory management. Let me start recording the Zoom also. Okay, Ismail, you can take it away from here.
Sure, cool. All right, well, this talk is going to be about mainly modern features of C++. We'll mainly talk about things that were introduced in C++ 11, 14, and I guess maybe 17. We'll also talk about memory management fundamentals and how memory really works at a low level so that it makes sense where you can optimize for performance or whatever. If you're contributing to open source, it's important to know this stuff. And let's get into it. So for me, regarding experience, I'm currently the DevOps and, well, the only one, the DevOps engineer for Royalty. I work in the cloud engineering team, handle a lot of the infrastructure work and a lot of automation and cloud native workspace. In regards to C++, I have experience working on 2D vector-based graphics engines. I was part of the main drawing team of the engine. Essentially, I implement the functionality that creates the possibility so you can render different curves and rotate them and then color them. That's the stuff I kind of worked on. I have, in regards to other C++ experience, I have been a previous contributor to Mod Organizer 2. If you have played Bethesda games like Fallout 4 or Skyrim or whatever, you may have heard of Mod Organizer 2. It's a very popular tool that's used. It makes a lot of things easier. And that was in C++ and Qt. And I'm currently one of the package maintainers on the AUR, the Arch user repositories, for Plumi. Plumi is an infrastructure as code tool. And essentially, since we use it for work, I sort of have to maintain it for myself to keep it up to date. And I basically publish on the AUR so that other people can use it as well. And my main experience lies around cloud native, system design, architecture, designing for scale, disaster recovery, stuff like this, a lot of automation related work. And with the help of C++, I do very low level work, close to the metal. If anyone cares about tech stack, I've a number of languages. I mean, there's C++, Python, Go, whatever. A lot of cloud related stuff, containerization, virtualization tools in there. Infrastructure as code with Ansible, Terraform, Plumi. Some build tools like CMake, Maven, yada, yada, yada. You've probably heard of this stuff. So moving on. So what will we strictly cover? We'll mainly cover a couple modern features of C++ that make certain things easy for you. And then we'll talk mainly about memory management. That will be one big topic. Undefined behavior, and it's going to come after memory management since they're tied in together. And we'll talk about that. We'll talk about, again, C++ specific things like null pointers. Then we'll talk about smart pointers and how you actually manage memory with those in a safe way. And at the end, we'll probably have maybe some questions. We might have different topics like intrinsics, or we might do live coding of like a vector container, like the standard library. Show you like how memory goes into play in this sense. All right, well, I'll refer back to the slides for explaining the specific topics, but from here on out, it should be basically live coding, and that should be it. All right, well, and if you have any questions along the way, it's better to ask while I'm explaining the example than wait till the end. But it's okay if you ask in the end as well. It doesn't make too much of a difference. Right, let's get into it. I had some basic code here, but we're going to delete this. So first we'll talk about the auto keyword. Auto was introduced in, I believe, C++ 11, and it lets you automatically deduct the type of a variable. So usually you have to be explicit and say something in string or whatever equals this or whatever. In the case of auto automatically detects it's a little bit verbose. The easier way to do this is, yeah, I believe you're not muted, but that's okay. A ranged for loop essentially lets you iterate over the variables without worrying about indexes or stuff. And you can do something like this, string A inside ABG. And I can now, you know, print out A.
Product and service. Я пак?
Just note, guys, someone's not muted, but I guess they don't realize that's okay. Arranged for the one thing to keep in mind.
Еми за Pain Reliever можем да напишем Good Price Quality Ratio, защото продуктите ни няма да са ефтини, ама ще са качествени.
Gracie, I believe you're not muted. Is there anything in the chat? That's funny.
Да.
Okay. That's hilarious. Right. The thing to keep in mind with ranged for loops, guys, is this actually takes a copy. So you're not actually accessing this thing. If I edit this, like if I changed ABG to none or whatever, this is actually not going to be reflected. So if I print out the first element in ABG, this is not going to be reflected because this just takes a copy from inside the vector. If you want to be able to modify that, what's inside the vector, I mean, you have to get a reference. So you have to get the actual variable. The nice thing here is you can use auto. Auto is just like useful in this case, and you can just add a reference to it, and this, you will be able to change, for example, the first variable. If I do this, it should be none, right? You can see here it's none. Those are for loops, ranged ones. Here we have lambdas. Lambdas are very much like arrow functions in JavaScript. If you're familiar with that, they work basically the same way, to the point that I might just write something in JavaScript and show that. And then we can look at the C++ example. In terms of, they are kind of like function pointers, but I'm not going to get into that because that might be confusing. You can basically create a function in place with a lambda and assign it to a variable. I can use auto f here, and then a lambda syntax is like so. This looks a bit confusing. So the first thing, these brackets, these are called capture statements. We'll get into this. The second one is just like a normal function. So the normal function here is the parameters it's going to take. There's literally no difference as if like you did this, right? If I write that, it's the same thing as I can write here. The last thing is the same as here. It's the function body, and basically to f, I have assigned a function, and I can call it with something, and you can see that it realizes that the function header is, it takes an integer. The nice part about lambdas is being able to quickly write like a function. You don't even have to save them anywhere. And if you don't want to assign them to a variable, you can invoke them immediately this way. So let's write an example that we can invoke instantly. So if I do standard cout, this should be fine. I can remove this variable here, and I can invoke it directly, and that will run just like a function. So the capture statement here usually takes two different possibilities. It's either an equals, or it takes an ampersand. And that is mainly for stuff like this. So if you notice, I cannot work with variables outside of this scope. It won't let me. This is causing a compiler error, and it's going to complain. Var cannot be implicitly captured because no default capture mode has been specified. It's talking about the capture statement. If I do it like so, this is captured by value. So it's a copy of var, right? Strictly var. It works, but I can't edit var, right? If I try this, I mean, well, first of all, it's not even letting me capture in this sense, but I cannot change it because it's, I cannot change this strict variable because it's copied by value. And here you take it by reference. So which one is better? If you can take it by reference, it's better to take it by reference because you avoid copying and you save CPU cycles, literally. Or if you have a couple of variables, so maybe you want to take one of them by value and you want to take one of them by copy. In this, well, one of them by value, one of them by reference. So if I take the string by reference, which is better, strings are slow to copy, but I can take the int as copy. So this works exactly as you would expect. If I changed name in here, that would affect this. If I change var here, it won't affect this because one is a copy, one is a reference. That's basically what lambdas are. You can just create a small function and just assign to a variable using auto. It's pretty simple to use. For each, and we'll talk about sort as well. We'll talk about both sort and for each. Okay, let's create a vector of integers, and we'll call it a, and this will be initializer list this. Just like that. For each just lets you operate on every single element in the whatever container you have. So if you have a vector or a list, it lets you operate on those. But at the end of the function, basically like definition, you can put a function for it to execute. So if it will basically execute whatever function you give it on every element. So you can embed a lot of complex logic into this. You used to have to use a function pointer, but now you can use lambdas. And that's why lambdas are nice. It's because you'll have to work with functions like sort, right? They will usually take lambdas, and that's where the logic kind of comes in handy. If I change the order here, And let's print this. We'll print it out before sorting and after sorting. So I'll do auto I in A, that's fine. And then we'll just print this out I, and we'll put a space. Cool. So this should print them as expected. Now we will sort here. So standard, this is obviously wants, that's annoying. It wants to do a quick sort. Let's see if we can include the algorithm library, because I believe sort should be there. There we go, sort. Sort takes an iterator. Well, it takes a beginning iterator and a last iterator. In the case of vectors, you can quickly get those with a.begin. And in this case, and finally here you can see I can pass a lambda to do the logic, essentially. And basically this is going to be my sorting logic. How do I want to sort this? So in the case of the lambda, it's going to get passed in two variables. I'm going to call it x and y. And then basically it should return, return whether x is bigger than y. And this should sort it. Works as expected. It's basically what's happening is at every stage, it's getting two variables and it returns the result of x is bigger than y. So it checks, is x bigger than y? Well, is 1 bigger than 6? No, it returns false. So then it does the sorting based on that logic, and therefore it does a descending sort. We can do ascending if I change this here. And that does an ascending sort. Another example would be, like we said, for each, if you want to do some kind of logic on every element. So standard for each, again, it's going to take an iterator. And then it takes a lambda again. Well, it can take a lambda. You can pass a function pointer, but lambdas are just easier to work with. And with for each, it's basically returning, because it's, working on every single element at a time. It basically takes in one variable. If you have like a more complex type than int, just use auto. It makes it easier. You have I here, and maybe obviously you can invoke a lot more complex logic here, but for the sake of this example, we will multiply every element in the list by 2. So it lets you iterate on all of them and pass a lambda to implement more complex logic. Deleted and defaulted functions. Okay, for this, this is the more object-oriented part of C++. So in C++, let's say I have a class foo, right? And maybe you have some private member in A or whatever. The thing is, you will very likely implement a constructor of some sort. The problem is, the right way to do it is you either implement no constructors, so you let the the compiler default them for you. It will create those for you if you don't declare any of them. If you explicitly declare any of them, that means you have to basically do 5 more things. You have your regular constructor that you just implemented, a default one. You have a parameterized one, very likely. Then you have a copy constructor, copy assignment operator, move constructor, and move assignment operator, and that you have to write yourself. If you want to explicitly declare the constructor and not write those, maybe I want to make the copy constructor. So we'll take a const foo reference, f, whatever. If I don't want to explicitly write this out, what I can do is default. And you can do it for the remaining 4. Essentially, this basically tells the compiler, implement the default functionality that you normally would. And if you want to, so if you're familiar with the singleton pattern, maybe some of you take software engineering. The idea is that with singletons, you're supposed to have one object and they can't be copied. To prevent copying, you normally would take the copy constructor and the copy assignment operator and put it in private. But C++, I believe 14 introduced this new concept of delete here. Essentially, it lets you basically say that we do not want these to be implemented. We want to prevent copying, so I'm going to put delete on my copy constructor. That's basically what it does. Constructor delegation. This is pretty simple. You delegate the work to another constructor. Okay. You might be familiar with this syntax. This is basically, again, an initializer list. So you can do stuff like this. You can initialize the variable pretty easily here, instead of just explicitly writing it out here. Just one thing, it might make sense to delegate the work to maybe another constructor, and then maybe here you set to var or whatever. And if you want to be able to do that, you just need to invoke like so. So basically, this delegates the work to the other parameterized constructor because it sees the second variable in the first variable in the parameter here that's being passed in, and it's like, okay, I'm just going to invoke this from constructor. This used to not be possible back in C++ 0.3, but that's a long while ago. And the main thing this lets you do is avoid repeating yourself. It's kind of syntactic sugar. Right, memory management. That's probably going to be a big one. Let's see. I'm going to switch to using namespace STD. Don't do this. It's not ideal, but I don't want to write all the namespaces. So what even is memory at this point? In C++, there are two types of memory. People will always say, well, C++ doesn't have automatic memory management. And that's kind of false. It does on the stack, not on the heap. And we'll explain what the stack and heap is. C++ has two types of memory. Like we said, stack and heap. Stack is self-managing, and it gets allocated at runtime of the program. And the problem with the stack is that the stack is static in size, and it cannot grow at runtime. And depending on your program, some functionality might require you to be able to grow a structure at runtime. Hence, for example, vectors, because vectors can reallocate themselves, they can grow in size, they can double in size, they can hold more items than a standard array. Standard arrays stuck with whatever size you give it. And vectors actually use the heap for this. So like we said, the stack is self-managing and it's scope-based. So what that means is if I have a function and I declare a variable here, outside the scope of this function, which is denoted by the curly braces, this variable does not exist. The memory gets freed when the function returns. Some people might ask, well, what happens if you return the variable? Doesn't that like kind of just live on? By the way, this is just IntelliSense being stupid. But essentially what's happening is you're not returning the variable, you're returning a copy. This is called value semantics, but that's a topic of its own. Essentially, when I declare a variable here, or even if I create a different scope, you can do something like this actually. Int AUBG equals 10. Outside of this scope, this variable does not exist. It gets automatically handled by the stack. It gets allocated, then deallocated, it's free, it's automatic. The heap is different. The heap, when you allocate any memory on the heap, the way it works is it lives on the heap until either one, the program exits, in which case all the memory is freed, or you explicitly free it. The point of the heap is if you have certain resources that need to live longer than the scope they're in, you should allocate them on the heap. And also, it prevents copying, because the thing with the stack is if you have larger types, the problem you're going to run into is you're going to constantly be copying them around. And even strings are slow to copy. You want to avoid copying as much as possible. So the nice thing about the heap is you can allocate on the heap, it's going to live there, and the only thing you need is a pointer to it. So a pointer is a memory address. You just have literally like an arrow pointing to that location on the memory. That's the point of the heap. Now the heap has disadvantages. The heap is allocating on the heap is very slow. You want to avoid heap allocations if you can. The stack is much better to allocate on. But since the stack is static in its size and it's stuck, essentially, you can blow it up. If you allocate too much on the stack, what's going to happen is you get a stack overflow, hence why that site exists in the first place. And even the icon is resembling a Stack Overflow. Essentially, the idea is if you allocate on the stack, a variable gets put on the stack. Once you're done with the variables it's going to get popped off the stack. It's automatic, but with the heap, it's different. We'll talk about heap allocations in the standard C way of doing things, which is, I guess, more ugly. We'll talk about the C++ way and how to do it with smart pointers. And we'll actually demonstrate the example of, this variable outside of this scope is not going to basically live. And I think for that, we have to look at the memory footprint. Right. So let's show that outside of this scope, that variable does not exist. I'm just going to call this func here. Doesn't matter. I'm going to print whatever here. This doesn't make much of a difference. I'm just putting in instructions. I'm going to do standard sin.get. This should make the console wait for input. And I'm going to put a couple of breakpoints here. And we'll go into memory debugging mode. And if we're in debugging mode, I run the debugger. And if you're not sure how to get to this memory layout, the way you do it is you go to debug, Windows, memory, and memory 1 is usually going to be enough. So this is the memory layout of the program. Right now, you can see a lot of it is just garbage. It's not initialized yet. So currently, we're calling this function. So if I continue, the variable is allocated. And I continue one more step. So the variable, well, actually, I should return one back. Let's go one back step, hopefully. OK, so now what I should be able to do is I can use the ampersand sign to go to the location of A. And if I go to the location of A, let's see if the variable is initialized at all. Here, it's not initialized. You can see C in, what's it called? Actually, let's just make this return like so. C in the debugging mode basically means the memory is initialized. And I need another breakpoint because this is not helping. Right. Should work as intended now. Variable is allocated, and now we move to return A. If I look to the location of A, you can see here, that is 4 bytes right there. In memory layout with hexadecimal, every byte is going to be represented with 2, well, basically symbols. So you can see it's initialized to 5. If I continue, we move down here, and this memory is basically going to get deallocated. I think it hasn't picked up on the fact that it is deallocated. And if I go again, you can see the memory is uninitialized now. It resets to 0 because it's popped off the stack. That's basically how that works. Let's look at a heap example and show that it doesn't actually get deallocated. So to allocate on the heap, we need a pointer. Essentially, we tell the computer to request some memory on the heap, and it allocates it and then returns a pointer to us. So I'm going to allocate a variable here. I'm going to use malloc. With malloc, I have to pass in how much memory to allocate, and this is in bytes. Off the top of your head, you might know an integer is 4 bytes usually, but the safest way to do it is use size of operator and pass in an int. So this should allocate 4 bytes of memory. Now malloc returns a void pointer, annoyingly, so you have to cast it to the type that you need. In our case, we need an int pointer, so I'm just going to cast it. And I'm going to make this return a pointer so we can prove that this will actually live on besides past its lifetime, basically. If that makes any sense. Close the console window, debugging mode. We're going to look at the memory layout again. Continue. The memory is going to be allocated here. Since it's a pointer, I don't have to use the ampersand sign. It's already a location. This is not initialized yet. Let's see if it's initialized now. There we go. So the variable A, you can see this is CD for now. Oh, wait, we forgot to initialize it to something. That's done. OK, we'll use 10 now. So I'm going to dereference, put a value on it. Local Windows debugger. There we go. Step over. Now we're at the allocation. Step over again. And if I look at the memory location of A, as you can see, it is 0A. A is essentially what you use in hexadecimal to denote 10. The memory is allocated here. And if you move, we're already at the standard cout, but you can see the memory is still there. There's nothing going on. And there's no change whatsoever because it's going to stay on the heap as long as we haven't freed the memory. Now, the standard C way of freeing the memory is using free. Yeah. And this will deallocate the memory for us. The C++ way is slightly cleaner. You will use the new operator. And new lets you call constructor. So I can call constructor of int to do this, and I don't have to even use this line. And in this case, if you're using C++ style pointers, you should not use free. Basically, you should use delete, and this will free the memory. That is roughly how stack and heap memory work. You can see it's mainly a question of lifetime changes, right? One can live on a lot longer. So if you think of a game, maybe you have some assets for the sky, they're loaded in, but the thing is, you may not want to copy those all around in different functions. You don't want to declare variables usually on the as global. That causes a lot of issues. The right way to do it is usually allocate on the heap and copy a pointer around, because a pointer, I mean, it's very small. It's 64 bits, 8 bytes. So 8 octets is very easy to copy around to maybe 100 megabyte block of memory than it is to copy the 100 megabyte of block of like memory around. The only problem with the heap is, well, when they were designing the language C and C++, they thought, well, you know, the programmers are pretty smart. They're going to manage their own memory. They know what they're doing. They'll free it properly. They won't cause issues. But that's not how it works, especially when you start passing pointers around. You start running into certain issues because sometimes you will free it in the wrong scope. Sometimes you won't free it at all. And when you don't free it at all, this is called a memory leak. And actually, Stefan sent me a meme about this, about a memory leak. And for those that don't know, so the way a memory leak works is that maybe you have a program and it does daily backups. So every 24 hours, it allocates some memory on the heap and it does a backup, but it forgets to free the memory. Let's say your program starts at 100 megabytes of RAM usage, and then every time it does a backup, it adds 50 megabytes more to that. Now, normally, if it was implemented properly, it would add the 50 megabytes, do what it needs to do, then free the memory. And then the program's memory footprint would move down to 100. The problem is when you forget to free and you have a memory leak, your program starts claiming more and more memory that it's not even using. And then at some point, the operating system is going to crash because it's going to run out of memory and it's not going to be able to malloc anything or use any new. And it's basically going to crash the entire thing. That's why memory leaks are dangerous. Now, people might say, well, when the program terminates, the memory is freed. That's true. But in a server environment, for example, certain programs need to run for days, weeks, months, sometimes years. If they're leaking even a couple megabytes of memory a day, in maybe 1 or 2 months, you're going to get some weird crashes and you might get corrupted data. It's going to cause a lot of issues. This is why it's important to deal with memory leaks and free your memory and manage this stuff in a smart way. Hence, they have introduced the concept of smart pointers in C++. With C++ 11, the idea of smart pointers is that they let you safely allocate on the heap, and the memory takes care of itself. And we can even, write this class ourselves, but as with usual with the standard library, you're probably not going to write a better implementation. Those guys usually know what they're doing. So smart pointers have 3 types. We're not going to probably talk about the last type. It doesn't have that much use. There's 2 types of it. The 2 main types. There's the unique pointer. The name implies that it can't be copied, and we'll explain why it can't be copied. And then there's the shared pointer, which is, just like a regular pointer. You can just pass it around. It's fine. So let's actually make a very simple class. I'm going to have this class foo. I'm going to have a constructor that will print out created, and we'll have a destructor. So the destructor syntax is going to be like so, and it's going to print out, let's see, it's going to print out deleted. Very basic behavior. So that should compile just fine, unless C++ doesn't want to behave. I think that's just IntelliSense errors. There were build errors. Where? It is, oh yeah, here it's missing a semicolon. Is that fine? Nope. Dereference, no, we're not dereferencing null pointers anymore. So the problem, oh, yeah, that's better. Okay, compiles just fine. Now we'll create, normally the way you would allocate an object of this on the heap is you create a foo pointer, PTR or whatever, and then you call it like so. And then you delete it. The smart pointer way of doing it is you can basically, you can do it the old way, which is, let's say, unique pointer. As you can see, then I put in the type, so type foo. And I might have a here, and then it calls a constructor maybe. Right, this is fine. There's a better way of doing this, and the suggested way now is just using auto with whatever variable name, and then you use standard make. So standard make unique for unique pointers and make shared for shared pointers. And this should take the same parameters, and here you can invoke the constructor. And that basically allocates memory on the heap. Now, we will actually show another example. I want to demonstrate that the fact that it manages its own memory. So I'm going to comment out this example, if I can. It doesn't want to be commented out. That's weird. Okay. And we'll do a regular example with a normal pointer. So pointer, new, foo, and I call the constructor. That's fine. Why are you complaining? What is this talking about? Nothing, it seems. Why is it? Is inaccessible. Why would that be inaccessible? That's an odd problem to run into.
You're having a class and everything's private.
Oh, yeah, you might be right. Thanks for that. I think that was Stefan. Yeah, by default, the behavior is everything's going to be private, but right now it should work just fine. And you can even invoke the constructor, not that it matters. In this case, there's not a parameterized constructor. But you can see it only runs created. Because the problem is this is allocated on the heap and it has to be managed manually. And basically, if I were to use delete here, it would actually invoke the constructor and free the memory. So let's show that example as well. I have to manage it myself. You can see created and then deleted. The example that we're showing here is the idea that this is self-managing. I don't have to deallocate it. And you can see it calls created and deleted. Essentially, the way it works is it allocates the memory. Once the memory runs out of scope, which the main function finishes, right? It runs out of scope and the memory is automatically freed. And for freeing, it calls delete, which will then call the destructor, which does everything you might need it to do. That's basically smart pointers. The thing with the unique pointers, it can't be copied around. Now, people might ask why. The reason it can't be copied around is that if I have, a function of some sort, and I have a unique, say, pointer of type foo that I take here, the problem we're going to run into is when we copy this over here, now I have this pointer existing in two scopes. One of them will finish first, right? Either the main function, well, main function cannot finish without this function finishing, basically. But the here, this function will finish first. It will go out of scope, and it will then free the memory. Now, in my main function, if I want to reuse that memory, this is called undefined behavior because the memory is already freed. If I dereference that pointer or do anything with it, the problem we're going to run into is that the standard does not define what should happen. Essentially, it's going to break. So unique pointer doesn't let this happen. They prevent copying. If you need to copy the pointer around, which is a very common case scenario, this is why you do it, you should use shared pointers. And the way shared pointers work is they have what's called a ref count, a reference count. So when you create it, it has a reference count of 1. When you copy it somewhere else, the reference count increases to 2. and the memory is not deallocated until the ref count hits 0. And the ref count gets reduced every time the copy goes out of scope. So if we copy it here, the ref count will be 2. Then the function will finish. Since it's finished and gone out of scope, essentially the ref count will go down to 1, but it will not free the memory because there's still references around, right? There's at least 1. And that's basically how smart pointers work. They let you basically allocate on the heap freely, and they basically manage the memory for you. This is the right way of doing things these days. Standard make unique and standard make shared. There's the last one, which is called weak pointer. Standard weak pointer. Now, the point of the weak pointer, no pun intended, Paul, is that it doesn't increase the ref count. You can use it to sometimes safely check if a pointer is alive, right? If the memory it's pointing at is alive. I haven't found many use cases for this. I've only mainly used unique pointers and shared pointers. That's just what makes sense to use. Just one thing, I guess this is more advanced, but for the curious ones among you, no, shared pointer is not thread safe. And if I literally pull up Paint, the idea with the shared pointer is that it has 2 components. And if I write here, shared pointer, right? Any shared pointer you have has 2 components to it. It has, this is the control block, right? This is our control block, and the control block controls the reference count, right? And controls when it's incremented, decremented. And this is the data we're actually dealing with, right? This is our data. The control block is thread safe. So if you pass it on to another thread, if you're making a multi-threaded application, this is fine. The ref count will increase and decrement properly, but the data you're looking at will actually not. You can still run into normal issues that you would run into with multi-threading. So you can have deadlocks, you can have undefined behavior because they're editing the same data at the same time. This stuff, you should use basically standard mutexes. If you're familiar with this stuff, this is outside of the scope of this talk, funnily enough. But you have to put a thread lock on it, work on whatever you need to do, and then free it. But that's a talk for another time, just saying it is not safe. It's not thread safe. Funnily enough, Facebook has a lot of bugs resulting in this, and they're like, oh, the moment we notice what the bug is when someone asks, oh, is shared pointer thread safe? And the answer is no, it's not thread safe. So let's talk about undefined behavior. And we'll talk about, some of you might be curious as to what's the difference between a pointer and a reference in C++, because they are very, very close and use cases slightly differ. But there are both like good reasons to use both of them. Now, undefined behavior is behavior of the language undefined by the C++ standard. So the old guys that make the standard, they decided, well, we don't know what should happen in this behavior. We're going to let the compiler decide. That's not ideal. The most common ways of undefined behavior is with memory. So if you have a pointer that is null and you dereference this, right? This is undefined behavior because it's a null pointer. I mean, the computer doesn't really know what to do with it. If you're on most Linux systems, this will cause a segmentation fault, and it's clearer to see. But in the case of Windows, it doesn't really do that. But you can see the error code is just this weird thing, and it just exits and it crashes, basically. And you can see IntelliSense is warning me. It says C6011 dereferencing null pointer, right? This is some things it picks up, but sometimes it's easier to go wrong with these. Now, the difference between C and C++ is that C++ has well, it's one of the differences. C++ has references and pointers. C only has pointers. So in C++, if I need to make a variable like AUBG, and I want to modify it in a different function, I'm just going to pass it by reference, right? I don't need necessarily a pointer for this. Well, just A. And I can basically change A to B, whatever, and this will actually affect it. The thing here is in C, they don't have this. So they would, even if, well, in the first place if they had strings at all, which they don't. They don't have strings like in C++. They're different in C. What they do is they have to pass pointers around all the time. The problem with passing pointers is you always have to check if it's null. If it's null, you can't do anything because it would be undefined behavior. And the great thing about references is they are guaranteed to be not null by the language. So if you use references, you don't have to check anything. You're guaranteed that it will work because if it is null, the compiler will complain in the first place. So you won't be able to run into weird bugs and create problems. So in terms of references and pointers, you have to ask yourself, can I use a pointer and a reference to do the same thing? And if the answer is yes, 9 out of 10 times you should use a reference. They're guaranteed to be safe. Pointers are not guaranteed to be safe. And the main reason you should ever use pointers is either some external library you're working with requires you to pass a pointer, or you want to allocate on the heap. That's the only reason for using pointers. If you want to edit a variable in place or in a different scope, you should use references. There's no point in using pointers. It makes no sense whatsoever. It makes a lot of sense in C because that's the only thing they have, but in the context of C++, this really just makes it harder. Other types of undefined behavior. So the first one was obviously dereferencing null pointer. The two most common ones after that is double free and access after free. So the idea is if I create a pointer and allocate memory and I set the variable to 5 and then I delete this, and basically what delete does is delete frees the memory. Now, this is terrible wording. Delete doesn't delete this variable. It only frees the memory it's pointing to. So this variable still exists here. And if I do something like this, right, if I try and access this, this is undefined behavior again, because this is called an access after free. The memory could have anything in there. It doesn't belong to us. So there could be garbage data. In some cases, this will print out something. So in this case, it doesn't. In some cases, you'll print out a garbage value because some other program is using it or whatever. But usually this will just crash the program. And the third type of undefined behavior is double free. And double free is essentially saying you called delete twice accidentally. And you might think to yourself, well, I'm not blind. I see like delete is happening beforehand. But when you're passing pointers around, one function might actually like free it at some point and the other might free it at some point. And this gets annoying with like this function manages its own memory, this function doesn't. So it can get pretty annoying, but these are the most common types of undefined behavior. And I'll actually show an example with standard vector, and we will create undefined behavior. So with standard vector, I'm just going to create A. And what I'm going to do is I'm going to create a reference to this. And I'm going to call it R, and it points to A. This is fine so far. There's nothing wrong with this. Now I'm going to go from 1 to 9, literally in numbers, or 10, doesn't matter. And I'm going to essentially do a.pushback, and I'm going to push the variable inside this. So I'm basically pushing from 0 to 9, I'm pushing the numbers into the vector. If I were to do this, right, well, I have to dereference here, I guess. Well, it's not letting me dereference. Let's just use a pointer here because this is annoying. Or, well, actually, it makes perfect sense because I just have to access it at a specific point. This is undefined behavior. Does anyone know why? This will not exactly work as intended, especially if I increase this number here. This will not work as intended. And here's why. The way vector works is that it allocates memory on the heap, right? And it has a default standard size it starts at. So I think it starts at 8 or 16 elements, something like that. You can see, well, this actually worked as intended. Let's switch to release mode. And in this case, this should not perfectly work, hopefully. Did the process code change? No, process 60. That is a bit odd. I guess the reserve is working. But essentially the idea with this one is once the vector goes above its size, it has to reallocate the memory somewhere else. And when it allocates the memory somewhere else, it frees the previous memory. Once the previous memory is freed, and if I try and access it, well, the problem I'm going to run into is I'm accessing memory that's no longer mine. It's allocated somewhere else. And we can show that it actually allocates memory using new. And I'm going to overload the new operator. And new takes a size in, size t. This is basically the standard implementation of new, as far as I know. And we'll make it print out whenever it allocates anything. And this is the kind of the stuff you don't exactly see unless you use something like this. So every time it allocates memory, I'm going to say allocating size bytes on the heap. Cool. And new line, and that should be fine. And I'm going to use the simplest implementation of this, which is with malloc in size. You're supposed to make this slightly smarter. I can show that example as well. But if you run this, what you're going to see is, first of all, it allocates 4 bytes on the heap for one element, for one integer. And then every time I push, the vector is reallocating itself constantly to new memory. And at this point, it's allocated 844 bytes. Like we talked, heap allocations are slow. So you want to avoid allocating this many times. And if you want to set it to a standard starting size, you can put 200 and it will start at 200. And if I run this, well, in this case, basically, since it starts at 200, it's gonna double every time it thinks that it needs to grow in size. That's basically what's happening. Or you can use what's called the reserve keyword. So I'm gonna reserve space for at least 200 ints. So you lower the amount of heap allocations. And here you can see I do a one-time allocation here for 200 integers. And in most platforms, an integer is 4 bytes, so it allocates 800 bytes. And it doesn't do heap allocations other than that. It just does one. And that this adds up, definitely. If it's a couple heap allocations, everything's fine. But if you start talking about like, well, we have 5,000 heap allocations, that's going to slow down the program a lot. And it helps to minimize these and lower these. String does the same. Actually, that's the reason strings can grow in size in the first place. Otherwise, like the memory doesn't have the concept of dynamic. It really doesn't. It's not as smart as you think. And the real way strings work is they work through heap allocations. And I believe in the C++ standard on release mode with optimizations enabled, a string will take 15 characters until it is heap allocated. Before that, it's basically going to be a const char pointer. It's static in size, but past the 15th mark, once you have more than 15 characters, so if I put a crap ton of characters in here, this will actually heap allocate. So this should do a heap allocation, let's see. And you can see allocating 48 bytes on the heap. If I reduce to exactly 15 characters, let's see, 1, 2, 3. So this is 15 characters. It allocated none on the heap. I think 15 is the exact number on Windows. Let's go to 16. And it allocates on the heap. Perfect. So 15 is the number. Now this is in release mode with optimizations enabled. In debug mode, it will always allocate on the heap. Now it's 15, it shouldn't, but it will because it's allocating. This is debug mode. It has debugging flags enabled. There's no compiler optimizations. And essentially it will heap allocate whatever it can. But that's basically how strings work and resize themselves. The way it works is it allocates on the heap. If it needs to grow in size, it will reallocate somewhere else. Right. And I guess we'll just talk about null pointers. And if there's any questions, we can talk about those. Now, funnily enough, in C, you will check for null, but in C++, you want to check for null pointer. And there's a good reason for this. If I have two functions with blueprints like so, right, and I have another overload of this with bool, and if I have finally a version that takes a pointer, a void pointer, for example, if I do something like this, I call this is kind of undefined behavior because this is not explicit enough. Funnily in C and even in C++, null can be treated like an integer because it's 0. It can be treated like a Boolean because it's 0 and 0 is implicitly false. And it can be, well, actually, no, I think it defaults to true. And it can be treated like a pointer. So in fact, depending on your compiler specifics, it can call any of these functions, and it might actually change from run to run. So one time it might run int, one time it might run the void pointer one. This is like undefined, it's not clear enough. But if I pass strictly null pointer, this will only invoke this one. So this is clear because, again, in C, null can mean a lot of things. You'll use null everywhere. You'll use for checking for strings, you'll check for integers even sometimes, and you'll check for pointers. In C++, this is not smart. You should use the null pointer keyword. It's guaranteed to call the one with pointer, and let's actually prove that it will call that one. Standard, I'll use printf, doesn't matter. I forgot the function I was going to use. Let's see if this actually works. It should. Yep, it calls that one. Now, I want to kind of show that it can call the other ones. I'm not sure if it's guaranteed, but we will find out, I guess, if I use null. The compiler might be smart enough. It might be stupid. I don't know. Sometimes it's very smart. It called int. Okay, that's funny. Yeah, if you pass null, it might call int. Let's see if it changes. No, because it's the first declaration. So if I cut this out, it will call Boolean now, actually, because it's the first thing it sees. Actually, it's not going to complain about something. What are you complaining about? Oh, so now none of them matches. So C++ doesn't let Boolean implicitly convert, I guess. That's funny.
Actually, the first one was an exact match. That's why, because it's an int. And it can convert to both of them. And it's ambiguous.
It's very ambiguous behavior. Yeah, that's true.
So it can convert to both. So that's why it can't call it. But here it can call exactly the proper function.
Yeah, you might be right. That's kind of, I wonder what happens at assembly level. That's kind of, wait.
No, it's a compiler. It doesn't go at assembly at all. On GCC, I think it would call the void star because it's defined in a different way. So
yeah,
it depends.
Yeah, it's a weird behavior. For those that are interested in dealing with annoying memory bugs, if you use Clang, you can use an address sanitizer. If you're on Linux platforms, you can use Valgrind, the tool. If I can maybe show you guys actually Valgrind. Yeah, valgrind.org. This is a very nice tool. Mainly it's meant for Linux systems, and it's because it uses some specific features of the Linux kernel. So you probably won't find this on Windows, but you can probably use it in WSL or in a virtual machine. In Windows, probably the best way is using Clang with memory, well, address sanitizer, and it will complain about certain stuff. And ownership changes, it might complain about those as well. But by default, the compiler is not as smart as you would think. It fails, especially when it comes to memory. So there can definitely be some issues. I'm wondering if there's anything else to talk about. This talk was definitely long, so if there's any questions, you can ask those, obviously. I guess we'll move on to the last slide. You can contact me on any of these emails or whatever. And you can ask questions whether it's relating to industry work, whether it's C++ or not. Frankly, I don't care whether you're interested in DevOps or like the work that I do. That's fine too. If anyone has specific issues, questions or whatever, you can ask those. That's fine. I'm hoping I haven't lost connection. That'd be hilarious. I'm going to look at the chat for this. Memory. Yeah, okay, it's fine. Stefan, is there any questions, or do you want me to maybe find the meme that you were talking about?
I wouldn't say any question. Like, I guess, which version do you primarily use in that case?
C++ versions?
Yeah, which version of the standard?
Mainly 14. I know that some people are moving to 17. I've seen the features of 17. Doesn't add too much. I will suggest staying away from 0.3 and 11 because 11 doesn't have some stuff that 14 has added and improved upon 11. Like it doesn't have standard make unique, right? Standard make unique is part of C++ 14. That's and it's nice to have those. I believe with the standard 11 unique pointers and stuff, you can run into exceptions. I think that was the main issue, but I don't exactly know what they improved. But I know for a fact you should be using the standard now. 14 is nice. 17 is nice. 20, it depends on your compiler implementation. I think Clang probably has some experimental builds that you can use. GCC probably has some experimental versions that implement 20. I haven't looked too much into the 20 standard. We'll see what happens. My problem with C++ is the language standard just keeps adding more and more. And now there's like a million ways of doing things. And, you know, with like vectors, you have iterators that you can use, like the old way. So you would have like standard, I think, iterator begin, and then you would have the end one. And then you would check if it's standard, iterator.end. And now you have range for loops. You can do index-based ones. There's way too many ways to do things. And that's mainly my problem with C++. Instead of improving on the previous things, they just keep on adding more. And that didn't work for C. I mean, if you keep up with C, C11 is not what people use. People use the 99 standard. And even though the 11 standard has been released 9 years ago at this point, people are not interested in using it, especially their thread API. People will use pthread over whatever C tried to implement in, I believe, was it C09 or 11? They implemented some stuff, but people don't like using those.
Well, actually, just give me perspective.
Can't quite hear you. I think.
Now, is it better?
No, it's still a bit too far.
Strange. Can the others hear me well, or did I?
Not really. It's
no.
really far.
1 sec.
You were fine a couple of minutes ago, like completely, but I don't know what happened now.
Now? Or?
Yeah, it's fine. It's okay. Now.
Okay. Okay, I guess I had to unmute. Which is to give some perspective, since you mentioned that on the standardization, since I'm technically part of it. So the reason for like having such a the additions to C++ and everything is because, and having a lot of things to use is backwards compatibility is a big thing for C++.
Yeah, obviously.
And you have to, you can't remove and add stuff. You can add, wait a bit, and then remove stuff. And typically, the idea of C++ to be kind of like, it's a paradigm, it's a sort of like a motto, not to leave a room for a language beneath it and the machine.
Yeah.
So it has to have such like nooks and like sort of like small things that you would eventually go down. So that's the reason. So and in C it's kind of a little bit different because also the C developers are a lot more conservative. So it is also a little bit of a social factor. Like the C11 things are superior to anything like used like without it. But it's just sort of like technically C++ developers took in C11 faster, like because it's integrated into the other standard than practical C developers. So it's kind of like
yeah, it's kind of also annoying that they used to have problems in the past so in C this used to be very valid code if you wrote without like main, without any specific thing. Mm-hmm. Like it is implicitly integer. C++ did not like that, so they had to wait for C standard to make it explicit, and then then you could have complete compatibility between C and C++. C has an interesting story. C++ tried to be this like we will beat C in every way, but it kind of ended up being its own language. And that's usually what happens when a technology tries to replace another one, is that they just become yet another technology, not usually a replacement. And C is used in different parts, obviously. And if you ask Linus Torvalds, that guy hates C++ and thinks it's an abomination. So.
Yeah. Oh, and also something else about the language standards. Actually, Visual Studio supports pretty much everything from C+20.
Yeah,
not everything, but a lot.
It should. I was looking at it a couple months ago, then it wasn't fully supported, but right now MSVC should support a majority of whatever there's to use. I just haven't moved. I think the standard right now is set to 17, I believe. Where is it on?
Yeah, it by default it should be. This.
Where's
no, it's in the project. Like
it's in project
here.
settings. Yeah, where's
in the compiler options, so it should be.
C++, general optimization language, that's permissive. Okay, ISO C++ 17 standard.
Yeah. And actually, regarding that, even though you said like it's good to people to stick, if you're doing a new project, just set it to the latest one. You typically not encounter it. Like,
yeah,
you're
17
unlikely.
and 20 is nice. Yeah, 17 and 20 is what I suggest. Just stay away from anything, but that's 11 or below. Just don't use those.
Yeah, definitely. Don't use Christos of B3, please. Don't. I'm serious.
Yeah. And there were also C++ is a weird landscape where it's one of the very few languages where certain projects will literally disable like half the language almost. If you didn't know, 30% of C++ projects disable exceptions. So that changes a lot of behavior because now you don't exactly have constructors, they're different things. And once you've gotten rid of exceptions, it becomes very much like C with error codes and stuff. And it's just like, why use C++ at that point? Some stay away from the C++ standard library. Some just use Boost for everything. It's very divisive, annoyingly. There's no right way to do anything. Yeah. Even with smart pointers, people argue you should still use raw ones sometimes. And
those people are wrong. Like, I'm just serious about especially that.
Right. Well, if there's any questions, cool. If there's not, I believe we'll end the talk here. I don't even know how long this has been going. Can anyone look at the timer? Just buy better. Well, no, maybe something with a better memory controller. But the problem is, if you're like doing huge allocations and just constantly freeing and allocating it slows down a lot of programs. And frankly, there are only two reasons to use C++. One, it's fast. Two, it's mature. Otherwise, stay away from C++. There are easier languages, and you don't have to deal with undefined behavior all the time. So that helps. But what is this? Yes, let's look at this. I love this. So there's this website called downloadmoreram.com, and it's absolutely perfect. I mean, this is just, and I love everyone knows the meme about you can just download more RAM, it works. But the funny thing is the timings are, I think, slightly wrong, and those voltages are crazy. That's 1.65. Mine is at 1.35, and it's supposed to be like an XMP profile that's overclocked. Where's CPUZ? This site, I need to buy this domain. I mean, I really need to, but it's going to be so expensive. So if the hub wants to maybe donate good money to a great cause, such as buying download more RAM, the domain, that would be great. If you look here, XMP profile, 1600 megahertz, cast latency 16 and 1.35 volts. Don't put 1.65, you will fry your RAM very likely. Or you won't, I don't know. I mean, maybe it will, maybe it won't work. But it should crash.
I also shared like why you can't download more RAM, the meme, like one of the memes. So it's probably about that.
Oh, what is this? Is this? Oh, yeah. So Stefan shared this meme about. This is gonna be so loud. Can I lower this? You can probably hear this. Basically, the idea is it's like me who forgot free in a loop, and then malloc. So malloc is allocating memory on the heap, and then you're supposed to free the memory that you're not using, so the memory is increasing, and boom, suck fault. It crashes your entire computer because one program has been eating up all the memory. Honestly, it sounds like Android Studio, because I think they just allocate memory they're not using, because that thing just chews through like 8 gigs of RAM or something. But yeah, basically that's it. And Jesus, I hate Visual Studio.